Alrighty, so today we're going to talk about one simple function, or one simple idea, and that is inverse functions. There is a little tidbit of calculus at the end. I'm going to show you two different ways to approach it. I have my own personal opinion on which way is better, but as always, I want to give you the option to use whichever one works better for you. Yeah, I'm talking to you memorizers in the crowd. Okay. So we're talking about inverse functions. What is an inverse function before we get into this? Be more specific. Well, good. Yeah. What's a dog? A dog is a dog. That's not a false statement. It's just not very accurate. Anybody else? You've all taken pre-calculus, right? Okay. So, for instance, what's the inverse function for a squared function?
Cube or square root.
Square root. What's the inverse function for addition? Good. And multiplication? Division. Okay, so again, what is an inverse function?
The opposite of.
All right, we'll go with it. That's fine. It's not horrible. I like it. All right, so we're going to talk about whether or not two functions are inverses of each other. Okay, so is x squared the inverse of the square root of x? Et cetera, et cetera. Obviously, they're going to be a little bit more complicated than that. All functions have inverses. However, not all of those inverses are functions. So that's an idea there that's going to trip some of you up. Let me say that once more. All functions have inverses. Not all of those inverses are functions. We want functions that have inverses that are also functions. So a function and an inverse function. Okay? So, for instance, let's take something like x squared.
I'm sorry, talking to
Don't be sorry, it's fine. If you imagine the graph of x squared, nice little looking parabola. If I turn that parabola on its side, it becomes the inverse function. But it is not an inverse function because it doesn't pass the vertical line test. So therefore, we cut part of it out and just use that single curve that you're used to for the square root function. We'll talk about more of that later. And then the calculus, we're going to find the derivative of inverse functions. And that's where I'm going to give you two options, whether you want to memorize a formula or whether or not you want to use a different technique that I will show you. And then today, simply be nice to people. Hopefully you've done this all day today. If you haven't, shame on you. If you have, good job. Okay, so this is a little bit of pre-calculus review. And I'm almost sure you did this in pre-calc, but the domain of a function is equal to the range of its inverse. And the range of the function is the domain of the inverse. So they flip each other out there. So in theory, if you want to find the range of something, instead of finding the range of a function, you could find the domain of the inverse and get the same results. The more important thing is number two. If you take a function and its inverse and you create a composite function, f of f inverse of x, if they are truly inverses, you should get x. They cancel each other out. So think about putting square root of x into x squared. The square root of anything squared is going to be itself, so you get back to x. And yes, you need to check both. You need to put the inverse into the function and the function in the inverse. They both give you x, then yep, those puppies are inverses of each other. But you knew this already, right? But you knew this already, right?
Of course I did.
Okay, good. Seriously, did your pre-calculus teachers teach you this? No? Let's not name names, just...
It's more algebra.
I think that's algebra 2.
No, we did that.
I know. Whatever. Doesn't matter. Let's move on. Good?
I still know nothing. It doesn't mean a lot.
Taking that egg on the road. Okay. Okay, two inverse functions. Well, I'm claiming they're inverse functions. I want to verify it. So just to make things a little less confusing, I called one f of x and I called the other one g of x. And to confirm that they are inverse functions of each other, I'm going to put one into the other. Actually, I'm going to do this both ways. I'm going to find f of g of x, and then in a lovely shade of blue, I'm going to find g of f of x. Let's do the red one first. Put g of x into f of x. I get 2 times the quantity, the cubic root, of x plus 1 over 2 cubed minus 1. I'll come back to that in a second. G of f of x, put f of x into g of x, I get the cubic root of 2x cubed minus 1 plus 1 over 2. Now the fun. Okay, I take a cubic root and cube it, I'll get just the function. And you're all fairly bright, so I think you'll see where I'll go from here. The 2's will cancel. X plus 1 minus 1 is x. Woohoo! Have to check the other one. I'm not going to do the cubic root for it. I'm going to do this. Negative 1 plus 1 is 0. That goes away. The 2's cancel. Now I have the cubic root of x cubed, which last time I checked is just x. Yippee-ki-yay, those are inverse functions. Are you good with that? Glad I could help. Go backward. If they both equal x. Have to equal x. Can't equal the same thing and have to equal x. Okay. So, blah, 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 blah. Okay. Now, this picture is very important because I don't know if you covered this, but if you look at f of x in that picture, I get a cubic function, which is what you're used to seeing. G of x is the inverse function of f of x. What's important is to look at the geometry here. If you take a function, its inverse will be the reflection of that graph over the line y equals x. That's really important for what we're going to do later. So the function and its inverse are reflections over the line y equals x, that 45-degree angle. Okay, so let's take a point on the original function f of x. Something easy like this. We'll call it a. A is at 0, negative 1. If I reflect the point A over the line y equals x, it will go to this point. We'll call it B. What's the relationship between the coordinates of A and the coordinates of B? No. Yeah, they're flipped. So the point xy becomes the point yx. So if I take, let's suppose this point here is, I don't know, 1 comma, I should be able to figure that out. Put 1 in there, 1 cubed is 2, and 1. Wait, why does that not look right? 1 cubed is 1 times 2 is 2 minus 1 is 1. This graph is hideous. Okay, so let's go 1 comma 17, just for giggles. That's not on the graph, you understand that. If I reflect the point 117 over the line y equals x, where does it go? 17. Beautiful. 17 comma 1. Okay. No signs changed. It just x and y switch spots. That's one of the basic ideas of the geometry behind inverse functions. Okay, so you reflect it, you're good to go. Which is exactly what that says. Okay. So, we now know how to get the picture of the inverse function. What we haven't talked about, well, and we talked about algebraically how to verify that they are inverses of each other. What we haven't talked about is whether or not that inverse is a function. So for instance, if I go back to this picture, is f of x a function? Yeah, how do you know? Say again? Beautiful. Vertical line test. F of x passes the vertical line test. In order for the inverse to also be a function, it has to pass the vertical line test. And that's a little tricky when we don't necessarily know what the inverse is, because later on we might not know what it is, but we still want to know whether or not the inverse is a function. And so we're going to use the horizontal line test. You've seen this before, right? Okay, vertical line test tests whether or not a function is whether or not a graph is a function. The horizontal line test tests whether or not a function's inverse is also a function. The process is exactly the same. If you can draw any horizontal line through a graph and it hits in more than one spot, its inverse is not a function. You can still draw a picture, except that that picture is not going to be a function. Okay, so again, if we go back to the idea, this is a little confusing, but if we go back to the idea of x squared, I take that graph of x squared and I flip it over the line y equals x, I get something that looks like this. So x squared is a function because it passes the vertical line test. However, x squared doesn't pass the horizontal line test, therefore its inverse is not a function. To combat that, what we do is frequently consider I erased the whole thing. Just consider this to be the square root. Okay, if you graph that on your calculator, the calculator will just graph the top half of that sideways parabola. Because it's looking for the part that is an inverse, it's looking for the inverse that is also a function. I hope I didn't confuse anybody with that. Good to go? Okay, good. So how do we do this? Well, practically speaking, you're going to use the horizontal line test. From a purely fancy schmancy calculus speak thing, you're concerned about two things. Is it one-to-one? Do you know what one-to-one means? Say again? Right. And each y goes to only one x. So it's got to be a what's that word? Reciprocal agreement. Every x has only one y, every y has only one x. And then part two, this is something new. If f is strictly monotonic, any idea what strictly monotonic means? I would be worried about you if you did. Strictly monotonic means that it is always increasing and always decreasing. In other words, there's no max or mins. So pretty much up to this point, we've done all pre-calculus. Now we can get some calculus involved in this and start saying, well, can I use calc to do all the stuff we've already done? Can I use calc to figure out if a inverse is a function? Can I use calc to figure out, well, pretty much that's what we're going to do. Everybody caught up? We good to go? Okay. So A and B. Now we could graph part A and then see if it passes the horizontal line test, but we can also do it with calculus. In order to do that, it has to be strictly monotonic, meaning it's always increasing or always decreasing. So in order to check that, I'm going to do f prime of x. F prime of x in this case is 3x squared plus 1. All right, what can you tell me about that derivative? It's a parabola. Anything else? Yes, it opens up. Good. Anything else? What's that?
It's always positive.
It's always positive. So if I try to solve for critical numbers to figure out where the maxes and mins are, hopefully you see that I would run into a big stumbling block here. 0 is equal to 3x squared plus 1, therefore 3x squared is equal to negative 1, so x squared is equal to negative 1/3, and remember we only deal with real numbers, so therefore that doesn't work. It's always positive, so it's always increasing, which means it's strictly monotonic. which means its inverse is a function. So get out your calculators or your Desmos on your iPads, graph that first function x cubed plus x minus 1 and confirm what we just figured out. Okay, so let me review what we just did. I am testing whether or not that inverse is a function. And I'm using calculus to do that. Okay, so pre-calculus would be what you got in your hand. You graph it, look at it, oh look, it passes the horizontal line test, I'm happy, let's move on. Calculus says it's got to be strictly monotonic, meaning it's always increasing or always decreasing. Well, in order for it to be always increasing or always decreasing, the derivative has to be either always positive or always negative. And since that derivative, as Ben pointed out, is always positive, no matter what I put in for x, I'm going to get a positive answer out of that. Then we know the function is always increasing, and therefore it's strictly monotonic, and therefore its inverse is a function. And when you look at the graph there, you should see that. Yes? Beautiful. Okay, part B. Now, you can pretty much assume that part B is not going to work out, because I designed it that way. So for part B, f prime of x is 3x squared minus 1. Set it equal to 0, and therefore x is equal to plus or minus the square root of 1/3. Which now all of a sudden I have critical numbers. If I have critical numbers, then there's a pretty good chance that the signs are going to change in there. And where would we go to from here? Well, I'd create a number line. This is my f prime number line. I'd put negative square root of 1/3 on there. I'd put the square root of 1/3 on there. Test some regions. Okay, I put in 0, for instance, I would get a negative number. It's decreasing. If I put in a big honking number there, it would be positive. And if I put in a big honking number, it would be positive. Now, all of a sudden, I know it's both increasing and decreasing. It's not strictly monotonic. Therefore, the inverse is not a function. So if you change your graph to match part B, x cubed minus x plus 1, you'll see that it does not pass the horizontal line test. It's more of what you expect on a traditional cubic graph. It's got the little upward bump and downward bump. Question?
So if you're asked this, do you have to do all the number line, or do you just say no?
I would probably, once I found that one region was positive and one region was negative, stop. You just need one example of it not being strictly monotonic and you're good to go. Okay, we good? Any other questions before we move on? Awesome. Okay, so, I happen to have some graphs here. There's the graph of f of x, passes the horizontal line test, its inverse is a function. Everybody's happy. Woohoo! Part B, like I said, does not pass the horizontal line test. Therefore, its inverse is not a function. It still has an inverse. I can take that picture and flip it over the line y equals x. 0, 1 would go to 1, 0. 1, 1 would stay where it is. Negative 1, 1 would go to 1, negative 1, blah, blah, blah. We'd have a picture. Everybody's happy. But that reflection would not be a function. Pregunta.
So pretty much part A was a function because there's those vertical points on it?
You got it.
Okay.
Always positive.
Okay.
Okay. Therefore, confirm that it does not, or sorry, confirm that its inverse is a function. HLT, horizontal line test, or derivatives. I would prefer derivatives. I think it's a little bit easier, especially if you don't have a graphing device, say on a test or a quiz. Now we want to find out what that is. Each one of these problems I've given you has been, here's a function and its inverse. What we haven't done is actually calculate the inverse, and you'll recall this from pre-calculus. Switch the x's and the y's, solve for y. What you're left with is the inverse. Okay. And I have an example of that here. I'd like to find the inverse of that function. So that's the same thing as y equals the square root of 2x minus 3, which means that x is equal to the square root of 2y minus 3. What's the first thing I do to solve for y?
Square it.
Square it. x squared is equal to 2y minus 3. Then what?
F.
Yeah, I'm assuming you would do this, so I'm just going to fly through it. And this would be f inverse of x. And we can go through that whole rigmarole we went through earlier where I could put f of x into f inverse of x, and I can put f inverse of x back into f. They will cancel each other out to get x. Question? Good? Beautiful. Okay, now the fun part. Blah, blah, blah. There's some pictures if you care. I don't think anybody does, so let's move on. Verify, yeah, verified. Okay, yeah, but you believe me. Okay, here we go. Now some new stuff. I'm going to take you through this first and show you the traditional approach to this, which involves, for those of you that are memorizers, probably something, a formula that's flashcard worthy. I would like to find the derivative, as it says, of an inverse function. So there's one method that we can do that I'm not really going to talk about except mentioning it, and that is we could just calculate the inverse, take the derivative, and be done with it. However, we're going to look at situations where you're looking for values on the derivative of the inverse. Okay, so let me just take you through this and show you what happens. There's the formula. So if I want to know the derivative of the inverse of x, that's comparable to 1 over f prime of f inverse of x. And to be honest, I don't use this at all, therefore it makes no sense to me. I like my method better, and you'll see why in a second. You don't have to do anything. This is America. Oh, right on.
Wait, which one's your last one?
Not that. I'll get to it. Okay, before I show you my method, we need a little bit of review. Tell me what a derivative is. Slope of the tangent line. Okay, so if I give you a function, you should have no trouble finding the slope of the tangent line, right? But that's not what you're asked to do. You're being asked to find the slope of the tangent line to the inverse function. So in other words, if I go back to this picture here, like a video game. That one. No, not that one. This one right there. If I ask you to find, there's a lot of stuff going on in this picture, so bear with me. Suppose I ask you to find the derivative of that point right there. Let's call it Q. You could plug and chug into that formula, and again, I'm assuming that you would know what the value of Q is, and we're also assuming that you don't know what the functions are. In other words, I'm looking for the slope of this line. Are you all with me? Okay, good. That's what I'm asking for the derivative, the value of the derivative of the inverse at that point Q. I'm suggesting we not even deal with that. I'm going to deal with the original function. So if I give you the point Q, could you find this point P? Yeah, we talked about that already, right? The x and the y's change. And if you have a function, could you not find the slope of that tangent line? Right? So we did that the red stuff a long time ago. We've been doing it for months now. Find the slope of the tangent line at some point on the graph. The key to my method is just remembering one thing, and that is the relationship between the slopes of the red line and the blue line. And that relationship is always constant. The blue line and the red line have reciprocal slopes. Not opposite reciprocal slopes. They're not perpendicular, just reciprocal slopes. So if the slope of the red line is 4/3, slope of the blue line would be 3/4. And since a derivative is just a slope of a tangent line, if we can find the slope of one, we can find the slope of the other. Now, my method required a lot more explanation, but I think when you get into the practice of it, you're going to see that mine is a little bit easier. Requires less memorization. Again, if you're a memorizer, then go crazy on this guy. 35 slides down. That guy. Okay. Now, this will make more sense when you see it in action. So let's take this function. I'm going to forget about part A for a second. I'm going to go right to part B. I want to know what is f inverse prime of 3. In other words, what's the slope of the tangent line to the inverse when x equals 3? Okay? So that means that there is some point, I'm going to stay with my color scheme here. We'll use blue for the inverse function. So there is some point on the inverse, 3 comma something or another. I don't know what that point is. However, if 3 comma something or another is on the inverse, what's the corresponding point on the original function? Something comma 3. Beautiful. Changing colors here. We get, on the original function, I've got some point, something comma 3. Can you find that something there? Can you find the x value of that point? Now, plug it into the original function. Set that function equal to 3 and solve it. So 3 is equal to 1/4 x cubed plus x minus 1. So 1/4 x cubed plus x is equal to 4. Oh boy, that's not so easy to solve. All right, now what do we do? Let's cheat. Get out your calculators. Graph 1/4 x cubed plus x minus 1. And figure out what x value is going to give you a y value of 3. Two? Let's see, 2 cubed is 8. 8 times a fourth is 2. 2 plus 2 is 4. Bingo. Done. Well, look, it just happens to turn out to be something nice. You would think I would have planned that. So therefore, this point is 2. So the point 3,2 is on the inverse. The point 2,3 is on the function. What I need to now calculate is the slope of the tangent line to the original function at the point 2,3. Well, that's easy. F prime of x is equal to 3/4 x squared plus 1. And now I want to know f prime of 2. So that's 4. Did I do my math right? 2 squared 4 is 3. 3 plus 1, 4. Yeah. So the slope of the tangent line to the original function is 4. Its corresponding point is 3,2. I don't even care about that. If the slope of the tangent line to the function is 4, what's the slope of the tangent to the inverse? 1/4. Done. Just flip it over. So f inverse of the derivative at 3 is equal to 1/4. Okay, now I know that may have melted your brain. But think about it from a geometric or a graphical standpoint. I had to do a little bit of work at the front end to figure out where these two corresponding points are. But you know that the corresponding points are going to switch coordinates with each other. 2, 3, 3, 2. If you can find one of them, you can find the other one, you just switch the location. Then I worked with the original function. I took the derivative, I plugged in 2. That means I found the slope of the tangent line to the original function at 2. Its corresponding point is 3, so that allowed me to find the derivatives of an f inverse at 3 by just flipping it over. But again, if you want to use that, go ahead. I'm not saying you can't. I'm just saying, for me, this makes more sense. For you, this probably looks easier. But as you practice it more, you'll realize that this is a pretty easy technique. Common mistake here is people take opposite reciprocals. It's just a reciprocal. Just flip it over. Questions? That was fun, wasn't it?
Yeah.
Beautiful. There's all the work. Done. I don't know what all that is. Day 78. Okay. So, the quiz on Thursday. We pushed it back because tomorrow is the weird period with the 105 minutes in second period. I hope you like your second period class. You're filling out a survey. Wednesday or tomorrow, we'll just continue with another lesson. We're only spending one day on inverses. Tomorrow we'll have a new lesson. Thursday, the quiz will only cover 5.1 to 5.2. So this is 5.3, therefore not on the quiz. Up through day 77. Why did you throw your pen down? You want to fight?
So this
Cool.
stuff won't be on the quiz? yet?
This stuff, no. Good? Okay? Right, what do you want that?
No, the how to find the inverse function. So
This?
Derivative.
Back further? I'm getting there, hold on. That one, okay, there you go.
I don't know why I just saw it.
Give me 1 second, let me stop my recording here. Discard.